Okay, for this circuit, we want a differential equation governing the current through this capacitor I sub c for t greater than 0. Now, if I have a circuit with a capacitor in it, I'm going to automatically label the voltage across the capacitor because I know I'm going to be interested in that sooner or later. So that voltage is V sub c, and this current I sub c is going to be C 0.5 times dVc by dt. I'm not sure if that's going to be useful to me later, but I've got it written on my diagram so I don't have to think about it. Probably the first thing after I've dealt with my energy storage elements that I'm going to do with an op-amp circuit is to apply the op-amp rules. So if I assume that this is 0 volts, this voltage here is Vn, which means that this voltage here is Vn, since I have 0 volts across the input terminals. Let me call this node A. So with an op-amp circuit, usually I'll do KCL at the input terminals. So KCL at A. So Vn minus 0 volts over 10 ohms plus Vn minus Vc over 20 ohms is equal to 0. So multiplying through by 20, in grouping terms, I get 3Vn is equal to Vc, which is great, except that I don't want my equation in terms of Vc, I want my equation in terms of I sub c. Well, that's where this shows up. I sub c is 0.5 dVc by dt, which is 0.5 times the derivative with respect to time of V sub c, which is just 3Vn. So I sub c is 0.5 times 3 is 1.5 dVn by dt. Now this isn't required by the problem statement, but I'd kind of like to check to see if this equation is right. So let's say Vn is a constant, and let t go to infinity. Well, if Vn is a constant, dVn dt is 0, so under this case, I sub c is going to be 0 amps. In the original circuit, if Vn is a constant, and I let t go to infinity, and as t goes to infinity, if everything's constant, my capacitor is going to look like an open circuit. So if the capacitor looks like an open circuit, I sub c will be 0, and that's perfectly consistent with what I got over here, so I can feel pretty good about this differential equation.